everybody? Mr. Poley here, back with yet another installment of Algebra 2. And today we're going to be learning about inverses of linear functions. So we've recently spent time learning about general inverses of functions, okay, and how to figure out if a function has an inverse that's also a function and what those relationships are all about. Today, though, is specifically taking it a little bit further, and now we're specifically looking at inverses of linear functions. Okay? So recall, first of all, that any function, will have an inverse that is also a function. A function will have an inverse that is also a function if that original function is 1-to-1. Okay, that's the only way a function can have an inverse that's also a function if that original function is 1-to-1. So with the exception of horizontal lines or horizontal line, which would clearly not be a 1-to-1 function because there's no way it could pass the horizontal line test if it's a horizontal line itself. So with the exception of horizontal lines, all linear functions are 1-to-1 functions, thus all of their inverses are also functions. So in this lesson, we are going to be investigating these inverses and how to find their equations. Okay, so there's two big ideas that we need to be successful in this lesson today. And they're ideas that you've already somewhat mastered. Okay, you need to know how to solve equations. Raise your hand if you can solve equations. Everybody should be raising their hand. We can all do that. Okay? You need to be able to solve equations, and you also need to remember the big idea of an inverse function. That's what I like to call the old switcheroo. When x and y switch places, that is how you can find an inverse function. Okay, so those are the big ideas we're going to be working with for this lesson today. Okay, so we're going to dive right in here and we'll see what we're working with. So on the grid below for exercise 1, on this grid right here, the linear function y equals 2x minus 4 is graphed along with the line y equals x. Okay, this is the line y equals 2x minus 4. This is the line y equals x. As we can tell from their labels, just like I always tell you guys, make sure you label your graphs, your functions. They're already labeled here. So you know that's the thing to do. Okay? How can you quickly tell that y equals 2x minus 4? How can you quickly tell this is a 1-to-1 function? How do we know? Real quick. Or if maybe we can't tell, what can we do? You can use the horizontal line test. So we know that this line here, this linear function, y equals 2x minus 4, we know it's 1-to-1 because it passes the good old HLT. Okay, the horizontal line test tells us this is 1-to-1. So now we're going to graph the inverse of y equals 2x minus 4 on the same grid. And here they tell us to recall that this is easily done by switching the x and y coordinates of the original line. Okay, the old switcheroo, again, just like I mentioned. So we want to take each of these points here that we can see clearly plotted on this line, and we want to reverse the x and y coordinates, switch those x and y coordinates, so that we can get the inverse function of this original function. Okay? So right now, I'm just going to write in the coordinates of each of these points. So this one here is -1, -6. This one is -4, 0. This one is 1, -2. Maybe I'm going to write these out here. So I'm not fighting with these grid lines here, right? -1, -6. Oops. Oh, technology. Gotta love it, right, guys? -4, 0. 1, -2. 2, 0. 3, 2. 4, 4. 5, 5, 6. 5, 6. Okay, those are the points that I can see on my original line. So now I'm going to reverse each one. Like I said, the old switcheroo. And I'm going to plot those. So -1, -6 becomes -6, -1. -4, 0. Did anybody catch that? Did anybody catch that? I wrote -4, 0 here, but that would be this point here. So, no way, Mr. Poley. That's just not the right point. I jumped right to the inverse. That original point was 0, -4. So that then becomes -4, 0. So I don't know if that was a silly brain fart, if I was already thinking about the inverse. It was a little mistake there. So I hope you guys were paying attention. I hope you guys didn't just blindly copy that down. You should have thought, wait a second, that's just not right. Mr. Poley, what are you doing? That's what I was doing. Okay, now we got it. So 0, -4 becomes -4, 0. 1, -2 becomes -2, 1. Maybe you guys can start to see this pattern that's happening here, right? Since it's a line, we know there's a constant slope. 2, 0 becomes 0, 2. Okay, it looks like I'm going up 1 over 2 each time. So I'm going to continue that pattern without even switching the rest of these points, because I know that has to be true. Now again, using your straight edge, draw that line through there. All right. So what can be said about the graphs of y equals 2x minus 4, so this original line that was here, and its inverse? This is now its inverse. Maybe I'll put a little y -1 to denote that that is the inverse function. So what can be said about the original and its inverse with respect to this line, y equals x? Do you guys see that relationship? I hope you do. We're bringing back a little geometry here. Geometry is fun. Okay? So they are symmetrical. They are symmetrical over y equals x. Right, so you guys see that here, this y equals x, that diagonal line straight through the origin from the very bottom left to the very top right. Okay, the original and its inverse are symmetrical over that line. Okay, it's like the original is reflected to be the inverse. Okay, I'm going to write in, it's a reflection. So it's a reflection. They are symmetrical over the line y equals x. Okay, and that is true for every function and its inverse. No matter if it's linear, quadratic, exponential, or whatever. A function and its inverse will always be symmetrical over the line y equals x. Like I said, it's a reflection over that line. And if anybody out there can recall or remember from geometry, a reflection over this line y equals x has the effect of switching the x and the y, which is what we've been learning about inverses all along. Okay, so there's a connection there to geometry. That's good stuff. The reflection over that line switches x and y. This should have been down here. Oy vey. Oy vey, you guys. Okay, they're symmetrical over y equals x. It is a reflection. Whoa. Now we have to find the equation of the inverse in y equals mx plus b form. So again, remember, if we're looking to get y equals mx, y equals mx plus b, what two things do we need? We need the slope and the y-intercept. If you guys remember, I used that pattern. I used the slope to finish plotting those points. I noticed we were going up 1 over 2. So that gives me a slope of 1 over 2, or 1/2. Remember that rise over run. Y equals 1/2 x. And my y-intercept I can see very clearly is at y equals 2. So 1/2 x plus 2 is the equation of this inverse. You can label that there. Okay. And again, I wrote that equation just based on the graph. But now we're going to do a little tiny manipulation to find this equation in this form here. Y equals x plus b over a. And you'll see once we get it in this form, it gives a more clear connection between the original and its inverse. So let's see how this works. I'll walk you through how we do this here. Y equals 1/2 x plus 2. If we want this to be in this form, this is showing a common denominator, because it's 2 terms on top over 1 denominator. So I need to get these 2 terms to have the same denominator. So since this one already has a denominator, since there's a fraction involved, I want this to have a denominator of 2. So I need 2 to be represented as a fraction over 2. And if that's not obvious right away, in order to figure that out, I can simply multiply that by 2 over 2. So multiplying by 2 over 2 is the same as multiplying by 1, because 2 divided by 2 is 1. So I'm not changing anything here. I'm just manipulating it to my advantage. And by multiplying by 2 over 2, that will give 2 terms then with the same denominator. So I have y equals 1/2 x plus 4 over 2. I can rewrite that. Hate that I run out of room here. They don't make these big enough for me. So I'm going to rewrite that as y equals x over 2. So that's the same as 1/2 x. 1/2 times x is x over 2 plus 4 over 2. And now I can combine that over one denominator to be x plus 4 over 2. So now my equation here is in that form. Y equals x plus 4 over 2. And now take a look at this equation, which again is the equation of my inverse, and look at the original equation. We started with y equals 2x minus 4. We ended with y equals x plus 4 divided by 2. Do you guys see what's happening here? Do you see this connection, this pattern? Right, comparing that to y equals 2x minus 4. What do we notice here? Okay, an inverse function includes the inverse operation, so the opposite operations of the original, but in opposite or reverse order. So keeping up that switcheroo, the reversal, right? Y equals 2x minus 4 shows 2 times x minus 4. 2 times x first, then subtract 4. Well, the inverse operation of subtracting 4 is adding 4. So our inverse starts by adding 4, where our original ended by subtracting 4. And then our inverse ends by dividing by 2 here, which is the inverse operation of multiplying by 2. So you can see those are inverse, original, inverse operations in the reverse order. X plus 4 instead of minus, divide by 2 instead of multiply. Okay, and that is a beautiful relationship there. One that applies across many different functions, many different situations. That's very cool how that works out. Just take a time, maybe pause here and think about that for a minute. Okay, examine it a little bit further. Make sure you're understanding what that relationship is. Okay? And based on that there with the inverse operations in the reverse order, right here we have a good note. This gives rise to a simple method of finding the equation of any inverse. Oh, what's that? You say there's a simple method? Well, let's see if that's true. Simply switch the x and y variables, which we know how to do like the back of our hand. Switch the x and y variables in the original equation and solve for y. Okay, so there's where those two big ideas that I mentioned in the beginning come into play. Switching x and y, and then solving an equation for y. So let's see how that plays out here in this first exercise. We have y equals 5x minus 20. So what was the first thing that we said we needed to do? Switch x and y. And to do that, you literally put x where y was and put y where x was. So I have x equals 5y minus 20. Okay, that's the first step. If you think that's too easy, that's good. It should be easy. You're just switching places. Now we need to solve for y, though. Okay, we have to solve for y in terms of x. Because we need an equation like what we're used to. Y equals mx plus b. That's what we're looking for. So I'm going to start, like you guys know here, by adding 20 to both sides. So I have x plus 20 equals 5y. Okay, because I'm trying to get y alone here. That's what I want all by itself in the end. So I have x plus 20 equals 5y. There's one last step, guys. One last step. Okay, 5y. Those are being multiplied. Means I need to divide by 5. So I'm going to write it like this. Actually, I'm not. I'm not going to write it like that. Okay, although that would not be wrong, of course, because both of those, that whole thing is being divided by 5. But if that whole thing is being divided by 5, we can divide each of those separately, which will help us get an equation in that proper y equals mx plus b form. So 5y divided by 5 leaves us with y, x over 5. Similar to up here where we had 1/2 x was the same as x over 2. Well, x over 5 is the same as 1/5 x. So I have y equals 1/5 x plus 20 over 5, which reduces very nicely to 4. So y equals 1/5 x plus 4 is my answer here. That's the inverse of this equation. Okay, y equals 5x minus 20. Y equals 5x minus 20. And maybe let's just verify that real quick, shall we? We shall. Okay, I'm going to type in 5x minus 20. Y equals 5x minus 20. I'm entering my original in here. And then I'm going to put in, I'm going to put in my inverse now. So I have 1/5 x plus 4. Remember, if you want to get that fraction input, press math, y equals, and then enter that. N over d stands for numerator over denominator, which that is a fraction. Okay, so I have y equals 5x minus 20 and y1, and then y2. All right, I know that's bright. It's 1/5 x plus 4. And now I'm going to press zoom 6 because I want to get that standard window. I want to get that standard window. And you guys, if you had those equations entered correctly, well, this is a struggle here to get this shown to you. All right, there is what your graph should look like. And there's one more I'm going to enter in here. For that y3, I'm going to put in y equals x. Okay, because that will give me the best visual to show that symmetry that we mentioned before. So hopefully you guys can see on your calculator at least if mine's too bright or blurry. Okay, the blue and red lines, which were my original function and my inverse, those are symmetrical over that line y equals x, which is the black line there. Okay, those are reflections of each other over that line. We got those because x and y were reversed. Inverse operations were in play. All right, so just to verify there and hopefully get you guys to trust me more on that fact. All right, you can check those every time to see, to make sure. All right, so on the back here, let's go, let's go. All right, so of course, when we do anything in math, especially something that's more procedural like the inverse functions, okay, switching x and y and then solving for y, that is a process, so that is procedural. And with things like that, certain problems can lead to common errors when solving for y. Okay, that's just something that happens. From my years teaching and other teachers teaching these concepts, we see it all the time. And that's okay. We're prepared for that. So, as always, I just heed the caution. Be careful. Watch your steps. Make sure what you're doing makes sense with what you already have. So, which of the following represents the inverse of the linear function y equals 2/3 x plus 8? Okay, first things first, if we're trying to find the inverse, you want to think switcheroo. Let's switch those x and y's. I have x equals 2/3 y plus 8. Okay, my first step would be to subtract 8. I have x minus 8 equals 2/3 y. All right, now we're dealing with a fraction coefficient, huh? 2/3 y. Not just 2y, not just 3y, but 2/3 y. So we can either divide by 2/3, like we're used to dividing by that coefficient, or we can multiply by the reciprocal, which that's what I prefer to do. And the reciprocal is the same fraction flipped. So if I have 2/3 y and I want to get rid of that, I multiply by 3/2. Because 2/3 times 3/2, the 3's will eliminate and the 2's will eliminate, leaving us with y. But that's not all. Oh, no. We also have to multiply this side by 3/2. Okay, and that's this whole thing here. So each of these terms has to be multiplied by 3/2. So that's why I put that in parentheses and the 3/2 in front. That 3/2 needs to be distributed to each of those two terms. So 3/2 times x is 3/2 x, or 3/2x. And then 3/2 times -8 will be minus 12. 3 times -8 is -24. Divided by 2 is -12. And that equals y. So y equals 3/2 x minus 12. That is choice 2. And again, I'm not going to show it now, but I think it would be great for you guys to pause it here and enter our original and what we came up with for the inverse, enter those into y equals with that line y equals x to verify that they are in fact symmetrical over that line. Okay. Exercise 4, what is the y-intercept of the inverse of y equals 3/5 x minus 9? Okay, the y-intercept of the inverse. So since we're trying to get practice here, coming up with the inverse equations, the inverse functions, by going through that process, that's what I'm going to attack again. So the first thing, I need to get the equation of my inverse. So y equals 3/5 x minus 9. I start by switching x and y. X equals 3/5 y minus 9. And now we know we need to add 9 to both sides. X plus 9 equals 3/5 y. Okay, and again, just like up here when I had 2/3 y, I multiplied by 3/2. Well, if now I have 3/5, I'm going to multiply by 5/3. Well, maybe that would be better for right now. Give myself a little more room. Okay, that side as well gets multiplied by 5/3. So 5/3 again, distribute into those two terms. 5/3 x plus 15, because 5 times 9 is 45. Divided by 3 is 15. And that is equal to y. Okay, so this is now our inverse. But we weren't just asked to find the equation of the inverse, but the y-intercept of the inverse. So this is when you need to quickly recall what is true about every y-intercept. Well, Mr. Poley, you would say, every y-intercept has an x-coordinate of 0. So that means I need to figure out when x is 0, what is y? And maybe something jumps out at you then just from looking at this. Okay, but when we plug in 0 here, 5/3 times 0 plus 15 equals y, anything times 0 is going to be 0. So that first term is totally gone, which means y, this board is being funny today, huh? That means y equals 15. That is the y-intercept. All right. Let's see. All right, one more question I want to do with you guys, or one more exercise, I should say. We're skipping 5 and 6 because those both deal with point slope form, and I chose not to get into that. So we're not doing 5 and 6. Again, you guys can thank me later for that. Exercise 7, last one here. And this brings up some previous knowledge, some prior knowledge here. Which of the following linear functions would not, key word there, which of the following would not have an inverse that is also a function? So you have y equals x, you have y equals 2, you have 2y equals x, you have y equals 5x minus 1. Okay? So maybe if you're not able to look at each of these and picture what their graph looks like or recognize what they look like on the graph, it would help to enter these all into y equals. Okay, this is y equals x, so we can enter that right away. Y equals 2 is good. 2y equals x needs to be manipulated a little bit. Try not to brighten this up. So we would divide both sides by 2 and get y equals 1/2 x. So now that one's good, that we can enter it. Y equals 5x minus 1. We can also enter those. Okay, so let's see. Boom, boom, boom. Get those entered in. So y equals x is y1. y2 is y equals 2. y3 is y equals 1/2 x, and y4 is 5x minus 1. So when we graph all of those, let's see what we're working with here. Should be 4 lines there, right? Which of those would not have an inverse that is also a function? Okay, everybody should be shouting, it's the red one. The red one can't have an inverse that's also a function. And which one is the red one? Well, let's look. Red is y equals 2. So our choice 3 here cannot have an inverse that is also a function. Okay, if you'll notice what kind of line that is a horizontal line, okay, through the point y equals 2. And like we mentioned in the beginning, every linear function will have an inverse that is also a function except for horizontal lines. Because this line y equals 2 fails the horizontal line test, which means it's not 1-to-1, which means its inverse cannot be a function. But all 3 of these other ones are diagonal lines. They are not horizontal, so they pass the horizontal line test, which means they're 1-to-1, which means they all have an inverse that is also a function. And that's about it. That's about it from me today on inverses of linear functions. I hope you guys are having some fun with this. And that's about it. All right, so thank you guys for watching. And I'll see you guys in class.